Today, I want to talk to you about my work on a very general problem, and that is, how do we understand high-dimensional systems? After all, at the center of almost every scientific discipline is a very large and very complicated system of interacting objects. Your brain, for example, has over 86 billion neurons. There are around 300 billion stars in the Milky Way galaxy, and ChatGPT-4 reportedly has over 1 trillion parameters. And all of these systems are amazing, and they're all capable of displaying incredible behavior, but they are hard to study. And the difficulty lies not only in their size, but in their intricate underlying structure. And the goal of my research is to quantify the role of that structure in generating complex phenomena. But before I dive into my work, let me convince you that this is actually an interesting problem, and that the structure really is important. Because, first of all, not every high-dimensional system is mysterious to us. Some systems can be understood very simply by looking at certain average quantities. And let me give you an example. So suppose someone handed you an extremely large number of water molecules, say something like 10 to the 23 of them, and they asked you if they were in a liquid state or a solid state. Now, you could very precisely try to figure out exactly what each one of these water molecules is doing, and you could try to build your answer that way, but that's a lot of water molecules, and that would probably take a very long time, and I just don't want to do that, Alternatively, you could compute the temperature, which is the average kinetic energy. And if the temperature is low enough, you know it's ice. So by looking at average quantities, we can reduce this massive high-dimensional system to just a handful of numbers, and that is really powerful. And these systems that can be understood very simply through these average quantities are called mean field systems. And the mathematical tools used to understand mean field systems are very powerful and very well understood. Unfortunately, many systems are not mean field. That is, they cannot be understood just by looking at these average quantities. And my favorite example of this is your brain. If we were to try to do the same thing and compute, say, the average electrical potential of all of the neurons in your brain, you would get garbage. And your brain is capable of all of these things, like thought and memory and emotion, and it would be absurd if we could understand all of that in the same way that we understood a glass of water. And I want to emphasize that the reason your brain is so interesting is not just because it has a lot of neurons, but because these neurons work together to form a very intricate structure. And it is the structure that allows for all of that sophisticated phenomena to emerge. And we call these systems that, like your brain, depend heavily on their structure, sparse networks. And the mathematical tools used to study sparse networks are not yet well developed. And that's where I come in. So the first thing to understand about sparse networks is the local behavior. That is, what does a small group of objects or particles do within this larger system? And to answer this question, we think about the problem in terms of energy. We know from physics that nature tends to favor states of low potential energy because those states are very stable. Think, for example, of a ball rolling down a hill. As the ball is rolling down the hill, it's lowering its own potential energy until it reaches the bottom of the hill where it achieves stability. And this principle of energy minimization is very nice, and it tells us that if we can understand the energy of a system, then we have a hope of understanding the dynamics of the system. So what I'm able to do is prove that this local group of particles works together to minimize an abstract version of energy. And to tell you about this abstract energy, I'm going to have to show you an equation. But I promise this is the only equation I'm going to show you today. So here we go. All right, this is our energy functional. And it's not exactly E equals mc squared, but let me try to break it down for you. So this first term corresponds to the classical physical energy. It's very well known to mathematicians and physicists, and to be honest, it's very reassuring that it appears here as well. And the second term is the one that I promised. This is the term that quantifies how structure is affecting the dynamics. You can think of it as a kind of penalty for the particles, for when they're being lazy and not doing anything interesting. And it is really the push and pull, the interaction of these two terms, that explain how these sparse networks might generate complex behavior. So there's a lot more I'd like to tell you about that energy function, maybe how we derived it, and most importantly, what we don't know about it yet. But that would take a lot more time and many, many more equations. And as far as the entire story of sparse networks goes, we're still very much at the beginning. But the point is this: if we want to understand the interesting and complex phenomena around us, it is crucial that we understand the role of structure. And this energy function, or rather my energy function, is an important step towards that direction. Thank you.